Morning, Doug, Ting, and Juan. Can you hear me okay?
Hello, Professor Nick. I have a question.
Yes.
Oh, it's the in the textbook program 102.
Yeah, you sent me an email, which I haven't
Oh yeah.
responded to. But let's see. 102, 108, 107, 104, 102. Yes. Okay. Can you wait and ask the question when we officially start class?
Oh, okay. Is that my question?
So, because I think that the question might be something other people have an interest in. So if we just wait and do it as part of class, that would be cool, if that's okay with you.
Okay, sure.
Because I think that's a really good question, but also a question that other people might have. And so we'll just make it part of class, and that'd be great.
Okay, thank you.
No problem. 9, 12, okay. Fogging up again. It's cold here, so my glasses are fogging up terribly. It's cold outside, so my glasses are cold. Hello, Darren. Okay, so let us go ahead and start. See if I can put my glasses on without them fogging up terribly. So good morning. Thank you for being cooperative about Friday. That turned out to be a good day for us. One of our teams came in second. That was very fun. It was sort of a strange thing being online instead of being in the place, but it worked out. So my primary goal today is to try to answer questions. I've got some things I can talk about, but I would expect that in wrestling with the assignment for Friday, that there are bound to be some questions that have come up. And Juan's got one, so we can start with that. But while I'm doing that one, I would encourage people to think about other questions you have about sound manipulation. And I would love to spend the whole day actually just talking about, just answering questions. So are there any big picture questions before we start with Juan's question as a starting point? Going. Okay, so Juan's got a question about program 102 in the book, and I've actually typed in a fragment of it that gets, I think, at the key thing. So, oops, it helps if I share, sorry. I forgot to join the meeting here in the room, and so nobody in the room was seeing the projector. But now we are projecting. So this is not the whole program. This is just the part that I think gets at your question. And Juan, if I'm not answering the right question by the end of this, definitely say so. But the example in chapter 8 merges words into a single sentence. So it takes two words and it takes a silence and it sort of joins them up to make a sentence. And I've left out a bunch of stuff here that's in the book because it's not really important to the question. Because Juan's question is, given these two loops, and tell me, Juan, if I'm misunderstanding the question, but given these two loops, Juan was concerned that the word Guzdial and the word is were going to be on top of each other instead of one after the other. The idea here is that this says Guzdial, and then there's a little silence, which I left out to make it all fit, is, and a little silence, and then you could say a frog or, whatever. So he set himself up for, whatever silly pranks you want to play. And Juan's concern is that the Guzdial sound and the is sound will copy onto the same location because they're both using index here to say where we are. Am I getting that right, Juan? Is that the correct question?
Yes.
Okay. So I think in some ways, this is a question of less than excellent naming in some ways. In particular, index here is, and this is not, no criticism of anybody in the class. This is a criticism specifically of the book, actually. I'm saying the book didn't name things well, and I think that naming made it harder to understand. And in particular, index is very vague about index of what, where, right? That could mean a lot of things. And in particular, we have 3 sound files we are working with, at least. There's the Guzdial sound file, there's the is sound file, and there's the target sound file, which is set up above, and I left that out in the interest of time. And so this index is an index into what, okay? And I don't think this name makes that very clear. And if we look at where it's used here and here. So in both cases, it's used as the index in the target for where we're writing a sample to, okay? So I would be inclined to rename this something like target index. And you'd have to do it everywhere, obviously. So that it's clearer. Oh, and then I have to do it here, and here, and here, and here. So it's clear that which index is this? This is the index into the target sound. This is where we're writing our values. And that this source is actually the index into the source sound. So again, to be consistent, I might say this really ought to be source index so that I'm using the word, I've got the word index everywhere to help make it clear that there's a source index and a target index, and they're not the same thing. One is a pointer into the source sound that we're copying from, and the other is an index into the target sound that we're copying to. And I want to be careful not to be overly critical of the book here. This is, you can find millions of pieces of code that have very similar naming conventions, and I'll bet good money you could find code that I've written in this class in front of all of you earlier in the semester that's got a very similar naming setup. Like that, I'm not always super consistent about this either, right? It's easy to just start typing and not necessarily think about how the names are going to affect people later on. But I do think in this case, using index and source to mean these similar things, but without providing any clarity about which one's which, or that even they're related. Right now, at least, target index and source index, having the word index in the names, suggests that there's a connection between these two things when there really wasn't one before. And so, well, okay, before we get to the actually answering Juan's question, did all this faffing about with names make sense? Questions about that? You good with that at home? Questions at home? Okay, then to get to Juan's question, these do not write on top of each other because we don't reset this back to 0 after this loop. So target index says where we're writing to in the target, and it starts at 0 and it increments every time we go through this loop. We don't reset it to 0. So when we write the next sample, we're writing it at a position 1 forward from the end of the previous sample. So it continues to move along because we don't set it back to the start. And so we could use this starting target index at 0 and incrementing in every loop. We could have dozens of loops, and each one would start where the last one left off, as long as we don't reset target index back to 0. And that's why the two sounds don't end up sitting on top of each other. Did that help? Cool. Good, good, good. So other questions about that? I mean, this is one of the things that this points out, and we've talked about it a little bit, and the book talks about it some, but I think it can be a source of confusion, is there's a lot of different ways you can write one of these loops. And sometimes we can loop over pixels or samples. Sometimes we loop over indices or XY coordinates. And they all have advantages and disadvantages. Here, being able to use an index and just continue to increment it as you move down the target file simplifies things in some ways, right? You don't have to kind of, otherwise there need to be like, if you started this back at 0 for this loop, you'd have to have like target index plus the length of the previous sound or something. It have to be some kind of offset addition to make sure we're writing into the correct place. And by just reusing target index over and over and making sure we don't reset it, we don't have to mess with that. Okay. Questions about that? Anything from the peeps at home? Okay. So then, how about some other questions? What other questions came up in sort of working on sound stuff doing the exercise? What kinds of questions do people have? Joseph.
So suppose we have two variables. We have the execution time and we have the length of the sound. So the relationship between when you execute a sound.
So if I'm understanding the question, I'll repeat it for the people at home and make sure you tell me if I'm getting it wrong. Is there a linear relationship between how long it takes to play a sound and the length of the sound in samples? Is that the question? And the answer is yes. So if we think about, there's the sampling rate is in samples per second. Okay. And so if the sampling rate is like 22,000 samples per second for many, and actually it's not quite that. Let me actually get a sound. Make sound, pick a file. Oh, we'll go back to our friend airplane. Play airplane. Oh. Oh, I didn't call it airplane, of course. I called it just sound. Airplane equals sound. Play airplane. Airplane. And people at home could hear airplane when it was played, correct? Thank you. Get sampling rate. Is 22,050. Okay. So so that means there's going to be 22,000 samples per second. So if the length of a sound is, and let's actually find the length of airplane. Come on, oh, come on, scroll down for me. Come on, work. What is your problem? Let's try this. Get length, there we go, airplane. So airplane is 14,503 samples. Okay. Then the time to play that sound is, and here we just have algebra-like word problems about how long does it take to drive from Cyrus to Starbuck if you're moving at 50 miles an hour. It's the same kind of thing. So we want time is samples divided by sampling rate. And if we think about how the units are going to play out here, samples divided by samples will cancel out. 1 over second will bring second up to the top, and we'll have seconds as the unit here. So that is, because we happen to have a calculator called Python, we can actually do this math. Oops, notice it did integer division. So that was not helpful. So we've got 0.658 seconds. So it's a linear relationship, and that this is exactly the math you would use to figure out how long something was. If you knew how many samples and you wanted to know how long it was, and you knew the sampling rate, division would get you there. And then flip side, if you knew how long you needed it to be and you knew the sampling rate, you could compute the number of samples by just reversing this algebra. But it is a linear relationship. There's a fixed number of samples per second, and so we don't have to worry about that. Now, so does that make sense? it can be in real life a little more complicated because most file formats involve some kind of compression. So like a WAV file is not strictly a list of sample values. And an image file like a JPEG is not strictly a bunch of RGB values. They do things to make those files smaller in a way that loses as little information as possible. Some compression formats don't lose anything at all. So there are compression formats that are called lossless, and that just means that they compress things, but in a way that doesn't lose any information. Most of the ones that you actually use are called lossy, L-O-S-S-Y, because they can get more compression in return for possibly losing a little information. And so, that relationship is not necessarily linear because certain things compress better than others. So as a simple example, if I'm looking at the room, okay, and actually if we think about the space behind me, because that's what people at home can see, a lot of that space is very uniform, right? The whiteboard, the painted area above the whiteboard, those are very uniform spaces. Those compress really well, and nothing's moving. So if we think about this from a moving picture perspective, if we were compressing a film, okay, my head moves, my hands occasionally sort of get up in the way, but all the background is really static here. Like nothing much is changing. So it's able to do a lot of compression there. If there was a lot of movement or a lot of detail, then it would be able to compress less. And so you may have actually seen this effect. I think it's a little less common now than it used to be, but sports often had TVs, especially like online streaming, often had a harder time with sports because everything moves all the time, right? There are almost no static shots. So a drama where two people sit and talk earnestly about important things, right? That compresses really beautifully because there's so little movement. But if you've got a basketball game that's moving very quickly end to end on the court, and the background's moving because the people are cheering and waving, right? It's very hard to compress that because there's not a lot that stays the same. So you can get very nonlinear relationships between compression and what's happening in a sound or an image. And to sort of come back to the sound thing, if there was a long quiet part in a symphony, say, that might compress a lot better than a section that has a lot of very fast changes in the music and sort of pitch and harmony and things like that. That would be harder to compress because there's a lot happening. And in the same way, the background here would compress better than, say, my face, because there's more detail in my face and my hair and stuff that we'd want to be able to reconstruct. So you can have nonlinear relationships depending on the content when you have compression. We're not going to get into compression algorithms here, but I think they're important because almost every piece of media you in fact deal with in the world has been compressed, because that's how we make it so we can move things around on the internet pretty efficiently. And so there can be nonlinear relationships there. In our world, everything's linear. So that was a longer answer than you probably expected, but I've been meaning to say something about that, and you gave me an excuse. So that answered the right question, plus some? Cool. Other questions? Somebody at home, there's got to be a question.
Maybe I wanted to like touch on how some compression formats, they compress it, but like there's really no perceivable difference. Like especially with photos, you can have one format that compresses it, another format that compresses it, and the detail is more or less the same.
So is the question about how two different compressions can yield very, very similar looking results?
Yeah. Like,
So-
is that I wanted to ask, like, what differences are there? Is that just like an efficiency thing, or why is it that some compression formats can be very similar, but they can have the same sizes, but they can look different, or they can have varying sizes and look the same?
So the question is like, how, in what ways, at least I think if I'm understanding Joshua's question, what ways do compression algorithms differ, and why do sometimes they lead to different outcomes, like things that look visually different, and other times two different compression algorithms can lead to things that look essentially the same? Is that more or less the right question?
Yeah.
Right. So I'm not going to go into this in too much detail because that's not really what this class is about, and I've probably talked about compression more than I should have already, but I will say a little bit. So two things. One is the issue of how can two compression algorithms yield very similar looking results is related to the question of how can a compression algorithm give you a picture or a sound that seems to be very much the same as the original uncompressed version. Because if we understand that, then the fact that there are two different compression algorithms that yield similar results, it basically follows from the fact that we can't usually tell the difference, that there's actually been any compression done. Then the other question of why do they look different sometimes is a slightly more complicated question. And the key piece, and we'll actually talk about this in a little more detail. Well, we might. I'm having to make some decisions. We'll probably have to cut some things out because we only have like a month-ish. We have a little more than a month left. I think we're running a little behind, which is totally fine. But it means there's going to have to be some cutting, and there's a piece we might cut that would be related to this. But the central thing is there's way more information in the sounds and the pictures than the human eye can usually really distinguish. In particular, if you think about 24-bit color, so 8 bits for red, 8 bits for green, 8 bits for blue. If we run back over to Jess, oops, come on, Jess. I need to be here. If we look at, 8 bits is 256 values. So that means that we can represent 16,777,216 different colors. That's an enormous number of colors, right? And most of us, even under the best of circumstances, probably can't distinguish 16 million different colors. And since most of the time we're not looking at the images that we're looking at all that closely, I mean, most of the time people have their phone, when they're looking at something, and they're half the time looking at their phone, right? You're definitely not discerning 16 million different colors. So if we compress by just reducing the color space a little bit, so instead of 16 million colors, let's say we remove 1 bit and then we can only represent 8 million colors. Well, that's still an awful lot of colors. And in most circumstances, you wouldn't be able to tell the difference. If you were an art photographer and you were making prints that would hang in, the Minnesota Institute of Art, right? You might care, but most people under most circumstances can't tell the difference. And the same thing happens with sound, right? We can represent 64,000 different amplitudes. That's a lot. And most of us aren't, under most circumstances, paying attention in a way that would remotely allow us to tell the difference. And so we can cut things down and get perfectly usable sound. I think one of the interesting sort of cultural pieces of the initial move to digital music in the 80s and 90s is the audio files were really, worked up about whether 44,000 samples a second was enough, whether we were losing information from LPs, and there were these lengthy fights. You can still find fragments of that happening now, but at the time, I mean, it was just holy war level shouting matches about the pros and cons of an LP versus a CD. And all of that missed the fact that what most, especially young people, cared about was cost, not quality. And when Napster came along and you could download things for free that you shouldn't technically legally have been downloading, but minor details, you could download things for free. And this is something like that you wouldn't be familiar with probably because of your age, but the quality of the sound files that people were getting from things like Napster and LimeWire and stuff like that in the 90s was terrible. I mean, these things had been super compressed to make them easier to move around on what was a very slow internet at the time. They'd often been recompressed and manipulated in various ways by God knows who along the way. They were awful sound files, truly terrible. But young people were like, I'll take that over paying, because you're making me pay a lot. And until really the iTunes store came into the world and you could buy the one song you wanted for $1. Up until that point, you had to buy whole albums. You wanted one song, you needed to spend $15 to get the album. People were like, I just want to hear this song a couple of times because it reminds me of, some date I went on or whatever. So I will download it from Napster and I don't care. And that was totally crushing everything else until Apple was like, we'll sell you one song. And then things like Spotify have moved that to the next level. It's like, we won't even sell you a song. We will just, sell you a service that lets you play whatever you want. And we'll give the artist like a fraction of a penny when we do that. And we'll call it a business model. And the artists are totally getting had in that deal, but no opinions being expressed here. So it was clear that, there were circumstances where quality was not the primary concern for a large part of the market. And I think that there were a lot of people that totally missed that fact. Okay, so that was a long rant about not really Yeshwant's question. So the other thing I'll say about Yeshwant's question about how things can look different sometimes, as an example, you've probably all interacted with PNG images and JPEG images. These should sound familiar. If you take something with sharp edges, actually a piece of text is a good example, and you use JPEG on it with a fairly high level of compression, you'll find that the sharp edges get weird little halos around them. They lose their sharpness in some way, but that PNGs don't do that. And it's just a matter, and maybe that's part of where Yeshwant's question is coming from, I don't know. But they're just, PNG and JPEG use a totally different approach to compression. And JPEG assumes it will be used on photographs where there's a lot of detail and change. And PNGs are really more aimed at documents. And a consequence of that is that a PNG preserves sharp edges much better than a JPEG does, because in nature, there aren't a lot of sharp edges. There's often gradient, even in things that might seem like sharp edges. And so JPEGs are not as, because of the assumptions that the JPEG algorithm makes, they just don't do a good job of preserving sharp edges, whereas PNGs, basically, PNG just counts runs of pixels that have the same value. And instead of saying pixel, 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 it says there are 27 pixels here with this red, green, and blue. And so it's like 27 and 3 numbers instead of 3 numbers 27 times. And that works for a PNG because if you imagine, like, let's say we made a PNG of this Jeff's file, all of this white is exactly the same RGB. So it'd be long stretches of this white. There are going to be significant stretches of this gray here in the middle, right? And then it just exactly captures where it goes from black to white. And so you get nice clean edges. Whereas JPEG does some very heavy math that we are not going to get into. But a consequence of that is it doesn't handle edges nearly as well. And if you crank up the JPEG compression, you definitely get artifacts around the edges. So. So Zeke's question is that why a lot of people use PNGs when they want transparent backgrounds? It could be part of it, but to be honest with you, I think part of it is that JPEGs don't actually support transparency. Whereas PNGs kind of have transparency built into them as a concept. I don't think JPEGs actually support transparency. Yeah, and so I don't think you can easily do transparency with JPEGs. So that's a concern. Yeah. And a standard way that transparency is handled, so we've been doing red, green, and blue as our three colors. They add a fourth color or channel called transparency or opacity, depends on how you want to phrase it. And it is how transparent is this pixel. It's called the alpha channel. And when alpha is high, then that pixel is very opaque, like you can't see through it if it's 1 or 255. And if it's 0, then it's completely transparent. You can see right through it. And that allows you to specify the transparency of pixels as well as their color. And that allows you to do some interesting things with overlaying images. And Jess doesn't support that, but that is a lot of, higher end drawing and image manipulation programs will support a notion of transparency, and that's how they handle that. So, okay, that was a very long answer to Yeshwant's question. Did that help, Yeshwant? Did that make sense? We are not hearing you. I think you're trying to say something because you're not muted, but we're not hearing you. You can just do a thumbs up unless you've got a follow-up question. Well, while Yeshwant's wrestling with his sound.
Yeah, that was good.
Okay.
Hello?
Continue.
Yeah, that was fine. My microphone died out, I guess.
I understand. I find myself banging around at mute buttons all the time at home, so I totally get that. Other questions about either what we've been talking about or more specifically things about Jess and sound? Joseph.
So about transparency, I think it's interesting how, so is it possible to represent transparency with RGB values?
So Joseph's question is, could you represent transparency with RGB values? And the answer is sort of no. I mean, the way one might think about doing it is by, instead of having white, having that be transparent, that lighter colors are transparent. But sometimes you actually want lighter colors and not see-through, right? Those are different things. And you really, so you could probably hack around it because you can hack around a lot of things. But if you really wanted it to work well, you really do need to treat that as a separate thing. Because you might want, let's say a light pink. A light pink was going to have a lot of white in it. It's red, but it has pretty high green and blue. So it's got a lot of white in it. A light pink, you might want to set that over a black background and have it be a nice contrasty light pink. You might want it to show up as a nice bright pink color there. If you treated white as transparency, you let a lot of the black bleed through. And now instead of a bright pink, you have something that's probably pretty hard to see. Like if you had a lot of white, instead of getting a nice contrast against that dark background, the dark background would overwhelm the small amount of color, and you probably wouldn't see anything at all. So you really do need a fourth channel. Now, a thing you could do if you said to yourself, okay, I don't want to have more than 24 bits per pixel, but I want transparency. You could say, okay, what if we do 6 bits of red, 6 of green, 6 of blue, and 6 of transparency? Or maybe even, you know, I mean, the division doesn't work out, but maybe like 4 bits of transparency, but then it doesn't divide evenly between 3 in the other colors, or 2 bits of transparency, that doesn't divide well either. So let's just stick with 6 of each. You could do that. There are technical reasons why people like having 8 bits for things. So computers process information in chunks. So a computer has a CPU. This goes back to, I think, chapter 1 talked about some of this stuff. So a computer has a CPU, which is the processing unit, the thing that does the math and the work. And it doesn't process things 1 bit at a time. It processes information in chunks. And the size of those chunks vary from computer to computer, but most computers these days are what are called 64-bit computers. You may actually have seen references to 64-bit versus 32-bit Windows, for example. So an older computer might have been a 32-bit computer, which meant that it processed 32 bits of information as a single piece. And one way to think about what that means, because it seems very abstract, is the hardware could add 2 32-bit numbers as a single step. A modern computer, I suspect all of the computers in this room, actually, those are 64-bit computers, so they could add 2 64-bit numbers in a single step. Because they can handle large chunks of information, we don't actually typically want to process like 6 bits. Because what we would be doing is we'd have 6 bits of information and another 58 bits of just emptiness. Because we have to process things in 64-bit chunks. And so we like groups of 8 because we can stack them up into a group of 64 and we can process them as whole bytes or whole chunks in single steps. And so for these kind of historical technical reasons, we tend to stick to whole round numbers of bytes for things like red, green, and blue. But there's no theoretical reason we couldn't take those 24 bits and divide them up into 4 6-bit chunks and say alpha is 6 bits, red, green, and blue are each 6 bits. That would work. It would just make doing the math more complicated on somebody else's end. That wouldn't have to be us, hopefully. But it could be made to work. So, and one of the reasons Jess is so slow compared to Photoshop or your favorite computer game, which does way more graphics rendering than Jess would ever imagine per frame, right, in real time, is that Jess is actually pulling out the red value and treating it as a single number with 8 bits of useful information and 56 bits of nothing. And then doing the same with the green, and then doing the same with the blue. So it's really handling everything one at a time. And a tool like Photoshop or any modern computer game is doing this sort of stuff in parallel. So it would fill that whole 64 bits with information from lots of different pixels, and it would process them at the same time, going through the hardware. And so it makes it way, way faster. And there's a lot more than that going on, but that's one of the many things that just doesn't do efficiently because it's designed as a teaching tool and not as a gaming engine that's gonna, make billions of dollars for EA or whatever, right? So that's a distinct difference. So, questions? Other questions? Going. there's one dangling question that's been, somebody asked in one of the Canvas questions several weeks ago, and it's an important question and I've never gotten to it. And so I want to actually talk about it. So I'm going to stop sharing that, which I probably should have done a long time ago. And I'm going to share my whiteboard. And it's the distinction between a method and a function, which I think isn't super clear necessarily. And so the idea is that we have some things that look like this. And then we have some things that look like, now I'm gapping one. I need to get an example. Momentary pause while I had a thing in mind and now it's left my brain. And see if I can find something quickly. May need to call and you all save me. No, these are not what I have in mind at all. So I know that this form has come up. Can somebody save me and remind me of a case where we've seen something that looks like this, thing dot thing? Go for it.
Append.
Append.
Or lower, upper.
That's right. So if we actually run back to Jess quick. So, and is it two lower or is it just lower? Nope. Let's just be lower. Yeah. So strings have methods upper and lower that convert all of their characters to respectively uppercase and lowercase. But instead of looking like lower hello, which doesn't work, right? They have this form hello dot lower. And this is, I'm using a string constant here, but if I said S was University of Minnesota Morris, and I said S dot upper, you would get Morris in shouty all caps, right? And S dot lower in all lowercase. Okay, so if we go back to my whiteboard. So so for example, stir dot lower. Okay. And so the question was sort of what's the difference between these and why do they both exist and what's going on? So a function is like a function in math. It's not connected to any particular value. It can take arguments and return a value. So len takes a string and returns a number, square takes a number and multiplies it by itself, et cetera, et cetera. A method is attached to a value called an object. And so this is using the word object as a technical term, not as just the English language word object. So in computer science, an object is a value and a related set of actions, say verbs or methods, attached to that value. So an object has particular things you can ask it to do, and it's specific to the kind of object. So a string, you can ask it to do lower or upper. Those are things strings know how to do. Pictures don't know how to do those things. Sounds don't know how to do those things. It doesn't make sense to talk about a sound being uppercase or lowercase, right? So they're tied to the type of the thing being worked with. And those calls have this form noun.verb, where noun is the object and verb is the method. I have to write that down. The call form is noun.verb, where noun is the object and verb is the method or action being called. And the book has worked pretty hard to do everything in functional form so far. All the things that act on pictures and sounds, for example, are functions. So we say things like get pixels, open paren, picture, close paren. Whereas you could imagine a universe where, so let's see if we actually say, the book uses functional forms, for example, get pixels, well, when it could have used a more object-oriented form, for example, picture.get pixels. And that's a choice the book made. The author, well, the book didn't make any choices. It's just, words on paper. But it's a choice the authors made to go with a functional approach rather than an object-oriented approach. The book introduces the idea of objects toward the end, and we will actually talk about that a little bit. This is one of the things I'm having to figure out in the sort of what gets cut and what gets kept question. But there is, at the very end, some nice material on turtles that uses this object-oriented form. And for any of you that go on to do more computer science, you will almost certainly deal a lot with this object style of programming. That's a very common way of organizing software these days. So languages like Java that you've perhaps heard of are object-oriented languages and rely heavily on this noun.verb approach. Python's interesting because it supports, in a fairly serious way, both functional style and object-oriented style. So we could do either one in Python. And I think the authors of the book felt that people were probably going to be more familiar with this notation from math classes and things like that. So they chose to organize the beginning material all in a functional form because they figured that they could avoid having to explain this notation here until later. I mean, I'm guessing here a little bit about their intention, but it seems like a reasonable approach to take. If you have been Googling Python stuff, because that's what human beings do when they're confused, is they ask Google questions. I mean, certainly, and I'm no different in that than anybody than you are. If you've been Googling stuff, you may well have seen this object style, which is, I think, where the question came from a few weeks ago, is that a student had been looking things up on the internet way back when we were talking about strings and had found some of these things and was like, whoa, what's going on? So that's the difference between those two things. And they're both a way of calling functions, okay? It's just that in one, the function goes first, and then the thing it acts on, the noun, goes second. And in the other, the noun comes first, and then the action comes after it. And this can take arguments. So the verb can take additional arguments if necessary. Upper and lower don't sort of have that example, but you could have situations where the verb takes some additional information. And that becomes an argument essentially to the function. And there's not a huge difference between them in some ways. The big thing is that here len is, no, don't do that. Here len is just floating in space, okay? And it just exists. And if we apply len to a number, we're going to get an error, right? Here, where's my example? Oh, I don't have it. I didn't write it down here. But like upper and lower are connected just to strings, and any string will have them, but not every string has them. And again, if you tried to call dot upper on a number, it's going to yell at you, or on a picture, it's going to yell at you. But you probably get a different error message. Let's actually go find out what that looks like. So I'm not off the top of my head sure. So if I say airplane dot lower, the error value is sound object has no attribute lower. So that's telling us airplane is a sound object and it has no attribute or method lower to call on it. Which is different from if we said lower airplane. Well, actually, no, I guess the more useful example would be like get a length of 7 instead of getting length of a sound. Here it says input is not a sound. So it's expecting 7 here to be a sound, and it wasn't. So in both cases, we're getting an error, but we're getting different sorts of errors. But they're not fundamentally different. They're both just saying we did the wrong thing. We sent the wrong information, had the wrong information in the wrong place. So that's the distinction between those two things. It mostly doesn't come up in the early part of the book unless you've been looking for things on the internet, which everybody does. But it will come up later on when we talk about object sum. So I wanted to sort of answer that. Did that make sense? Questions about that? Zeke. Yeah, so Zeke's question is, what are the advantages of objects versus just going with functions? The advantages are a little subtle for where we are right now. But here, I'll try to give you one. Oh, okay. Now here, I can come up with one that I think makes sense. If, let's imagine I wanted to have that function size that takes a media object and returns its size in bytes. Okay. That would seem to be a thing we might want to do. And it's something that makes sense for both pictures and sounds. A picture takes up a certain amount of space in bytes, a sound takes up a certain amount of space in bytes. So it's a question that seems coherent for both kinds of media that we've been looking at. In fact, we could ask the same question of a string. How many bytes do you take up, right? If we wrote this as a function, it would look something like if is picture item stuff elif is sound item stuff else, or let's say elif is string item stuff else, print unknown item type. Okay, that's me just making stuff up quickly, but it would look something like that. We'd have to say, is it a picture? If it is, do picture-y things to figure out how big it is. If it's a sound, do sound things to figure out how big it is. If it's a string, do string things to see how big it is, right? That'll work, but it's not super flexible. If we added a new kind of media, say we're like, oh, we're gonna support movies now. I've got to go in here and add another elif for movies. And let's say, oh, we're gonna have pictures with transparency. I've got to add an elif now to handle the pictures with transparency if they're going to be a distinct thing from pictures without transparency, right? So this function becomes this big chain of if, elif, 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 elif. And every time we add a new kind of media, we've got to go and stick another if in here, right? And it just doesn't scale well. So in the object land, we could say in object land, each version of size is defined for that object when that object is defined. So we'd have class picture def size picture stuff. Class sound def size sound stuff. Class other thing def size other thing stuff. And there's a lot of details here that I am totally glossing over because, we're not like trying to become experts at this yet. But we would define a new kind of thing with a class definition, okay? And a class can have one or more methods. Size would be one of those methods. And it would have whatever stuff is necessary to compute the size of a picture, okay? And by providing this size method, if we had a picture, we could say picture.size, and it would say which version of size do we need? We need the one that works for pictures, and it would use this one. And if we had a sound and we said sound.size, it would say, which one do we need? We need the one for sound, and it would use this one here. So we would avoid all this if stuff, and the system would basically do the if stuff for us. That when we call .size on something, it would look at what kind of thing is that, and it would route the size call to the correct definition, depending on the kind of thing that we had called size on. And so this can be a much more flexible way of building systems that have related behaviors, but you don't know in advance exactly how many kinds of things there might need to be. So that would be one advantage. Now there's ways to sort of get some of this behavior in function land, and you could again start a holy war on these kinds of questions in the wrong circles. And I definitely don't want to get into that, but that would be an advantage that people might see in objects. It's more complicated because there's all this extra machinery about classes and stuff like that, but it's sort of nice that you can have this related behavior separated out across a number of different classes. So did that help answer that question? Other questions? Questions about that? And did that help? I think it was Juan that had asked this question about methods versus functions a long time ago. That helped? Good. Cool. We've got 3 minutes left. Oh, yeah, 3 minutes left. Somebody should ask an awesome short question. Or even a not awesome short question. Anything? Okay, the sound collage assignment is due on Friday, and it's very similar to the image collage assignment. You have to take a bunch of sound pieces and stick them together, but on a sound instead of on a picture. But the idea is very much the same. So if you haven't looked at that, I definitely would. I have office hour slots tomorrow, and then we can spend as much of Wednesday answering questions about that as makes sense for people. So, Julio, any questions? Going. I think we're gonna call it good. Talk to everybody on Wednesday, or some of you maybe tomorrow.